All right, so part 2 of Unit 1, Lesson 5. We're continuing with this idea of average rate of change. In our last lesson, or our last video, we left off with what happens when you want to find the speed of an object or a rock at a particular instant in time. And that's going to be considered not an average rate of change, but an instantaneous rate of change. An instantaneous rate of, like an instantaneous speed is a moving body's instantaneous speed is its speed at a particular instance. And the best way I know to explain or describe that is, let's say that you're driving down the road and you see a highway patrol person and they're sitting on the side of the road and they're checking everyone's speed. So when he points his radar gun at your car and it pops up a speed, that is the speed at which you are traveling at that particular instant that he took that measurement. So we're going to be moving into this idea of an instantaneous rate of change versus an average rate of change. So before I talk about this scenario here, I want to put this in perspective. So our last example, we had d of t equals 16t squared, okay? We know that that is a quadratic that opens up and is very, very steep. So one of the things that we did was we wanted to find the average speed during the first 2 seconds of travel. And so let's say that this is 2, here's the point at 2, here is a point on the graph at 0, and because we were calculating an average speed and we calculated the change in distance divided by the change in time, which is slope, what in the world is that referring to? Well, that's referring to basically this little line that connects the point at t equals 0 and the point t equals 2. And so what we found that to be was, what did we find that to be? We found that to be 32. And so 32 feet per second was our value. Okay, the next one we did was I'll draw it again. Here's this. We looked at what was the average speed of the rock between 1 and 5. So here was 1, and let's say this is 5, and there's a point. We found that value to be 96. Well, what did the 96 represent? 96 feet per second. What that represented was the slope of the line that is connecting those 2 points. So an average rate of change is simply the average rate at which the distance was changing. Okay, so when we left off in the last video, we ran into the problem of trying to calculate an average speed, the average speed of the rock at t equals 2 seconds. And that, what happened was, I'm going to pull our last set of notes back in here. When we wanted to use the average approach to this, or the average rate of change, we noticed that when you use the actual time as your starting time and ending time, you ended up with 0 over 0. So let's talk about how then can we use this idea of an average speed to determine an instantaneous speed? Well, you need two time periods. You need a starting time and you need an ending time. And so if we want to calculate the average speed of the rock over the interval from time t equals 2 to some time slightly later, say t equals 2 plus h, then how can we utilize this idea of average speed? Well, we can do that or we can get a good idea of what is happening at t equals 2. So let's say, let me pull in something else. Okay, so at t equals 2, right here, or if you wanted to look at that one, if we wanted to know the actual speed of the rock at t equals 2, then what we would want is we would want to take a time that is slightly later. It could be anything that's later than 2 seconds. So what if we were to call that time 2 plus h? So if we can get an idea, of the average rate of change using t equals 2 and 2 plus h, then we might just get a good idea of how fast the rock was traveling at t equals 2 seconds. All right, so what the heck does that mean? Okay, so I'm going to redraw this. And since I'm talking about t equals 2, I'm going to act like a magnifying glass. I'm going to say this is 2. Here's a point at 2. There is a time that is greater or later than 2 that would have some value of 2 plus h. So here, I'll put that point. Now, that whole point right there could be 6. If it were 6, then the h would be 4. Okay, so we're just using this kind of in an abstract form. So let's talk about algebraically, how could we look at or use this average speed approach using values that are closer and closer to 2. All right, so let's just pick two values. We know we want to start with a time t equals 2, so our starting time is 2. We now need to have a time that is later than 2. I wouldn't make it 3. Let's make it 2.1. We'll make 2.1. That's pretty close to 2. So if this is 2 seconds and this is 2.1 seconds, we've got a decent idea. So I need my calculator, because I'm going to let the calculator do the work for me. So, but I'm going to set this up, and I'm going to scoot that up. So this would be d of 2.1 minus d of 2 divided by 2.1 minus 2. Okay, so I'm going to calculate the numerator, and remember our function was d of t equals 16t squared. So when I substitute 2.1 in for t, I have 16 parentheses 2.1, close it and square it, not x, back up, square, minus 16 times 2 squared. That should be the entire numerator. I'm going to press enter, and now I'm going to divide by 2.1 minus 2 is going to leave me with 0.1. So 0.1, enter. So here I have 65.6. Okay, so if this is 2 and this is 2.1, if this is 2 and this is 2.1, my average speed, or the average speed of the rock, would be about 65.6 feet per second. But let's see, can we get a number or a time that's even closer to 2? Well, how about t equals, we're going to continue with t equals 2, but what about t equals 2.01? Let's see what happens there. So this is d of 2.01 minus d of 2 divided by 2.01 minus 2. Is that right? Yeah, sorry. And so now I'm going to 16 times 2.01, close it and square. Why do I keep hitting X? And squaring it, minus 16 times 2 squared, and I will enter, and then I'm going to divide that by 2.01 minus 2 is 0.01, so 0.01, and enter. And so now I get 64.16 feet per second. So, okay, the average speed of the rock using points 2 and 2.01 yield or give us a speed of 64.16 feet per second. Well, what if we were to get even closer? So what if we do, y'all may not be able to see this very well, but how about between t equals 2 and t equals 2.001? So that would be d of 2.001 minus d of 2 divided by 2.001 minus 2. So going back to my calculator, 16 times 2.001, close, square, minus 16 times 2 squared, and I enter, and now I will divide by 0.001, 0.001. Oh, no. Something's not right. Hold on. All right, what did I do wrong? Answer divided by something doesn't look right. Oh, it's right there. I see it. It's right there. So I'm going to do second enter and second enter. And I'm going to go back and I'm going to delete that point. I will press enter. There we go. Now I will press divide by 0.001. Now I get a value of 64.016 feet per second. So let's just talk about what we've done. We wanted to know the speed of the rock at exactly 2 seconds. And so what we've done is we've said, okay, well of course we're starting with time 2. Let's calculate the average speed or average rate of change between time t equals 2 and time 2.1, okay? We did that, and we ended up with a speed of 65.6. Then we said, okay, well, what if we narrow that time gap even further? And we said, let's let t equal 2, and this time let's let the ending time be 2.01. This 2.01 is closer to 2 than 2.1 is. So the time interval here from 2 to 2.01 is smaller than this time. And we ended up with 64.16 feet per second. Then we said, okay, well, let's just close that gap even more. Let's close that time frame even more. And we said, let's look at what the average speed of the rock would be between t equals 2 and t equals 2.001. So the time difference between these two is smaller than the time difference between these two, which is smaller than the time difference between those two. And when we calculated that out, we ended up with 64.016 feet per second. Okay, so what if I wanted to get even closer? What if I wanted to close that time gap even further? And instead of writing it all out, I'll just go ahead and kind of do this on my calculator. I'm going to do second enter, and this time I'm going to go in and I'm going to insert a 0. So right above delete is INS, which means insert. Now I have the flashing cursor. I can enter 0. Now I don't need to do anything with that 2. I will go ahead and enter. Now let's talk about what we need to divide by. This time I would be subtracting the 2.001 minus the 2, and the difference would leave me with 0.0001, and I will press enter. So looking at these values, if I were to continue this, I would get another value that is 64.001, oops, not 4, but 6. So look at what is going on with these average speeds. These average speeds are decreasing and getting what appears to be very, very close to a specific value of 64. And how did we come up with those values? Well, we wanted to calculate the speed, the average speed of the rock, or the average speed between time intervals that get closer to 2, and the closer to 2 that we got, the closer our average speeds got to 64. So I want to talk about between 2 to 2.1. What is H? Ooh, we kind of got away from H for just a second. But what is H? So between 2 and 2.1, H equals 0.1. How about between 2 and 2.01? Well, H is equal to 0.01. How about between 2 and 2.001? Well, the H value is 0.001. When I calculated this on the calculator, the H value was 0.0001. If I were to continue this process, and by adding a 0 each time, my H value, notice what it's doing. My H values went from 0.1 to 0.01 to 0.001 to 0.0001 to 0.00001. So let's talk about how what is H doing? Well, H is approaching 0. H is getting smaller and smaller. In fact, it's decreasing and getting very close to 0. And at the same time, your ARC is getting closer and closer. I guess I should do an arrow. Your ARC is getting closer and closer to 64. So what does this sound like? What does this sound like? Sounds like limits to me. As H approaches something, Y approaches something. And so this is just an initial glimpse of how this limit, how average rates of change applies to limits. So let me put this in a geometric perspective. And this is going to be difficult because I don't have a big enough picture. So I'll tell you what I'm going to do. I'm going to get a bigger picture. I'm going to get a bigger piece of paper. I'm going to slide this over. And so here's what I want to do. I need to make this large. Here's 2. Here's 2. And this is going to be 2 plus h. Okay? Specifically, we said, let's let that be 2.1. Okay, when 2.1, that meant h was 0.1. Okay? When we found that value of 65.6, what did we find? We found the slope of the line between these 2 points. Okay, I'm actually going to write it here. H equals 0.1, and our slope was 65.6. Okay, then we said, okay, let's look at a time that's even closer to 2. So we did 2.01. Okay, well, here's the point, 2.01. So now we're looking at an h value. From here to here, the h value is 0.01, and we found that value to be, and that's, by the way, that's the slope of the line going through those 2 points, and we said that that value was 64, h equals 0.01, the slope or average rate of change was 64.16. Okay, we said let's get even closer, so 2.001, and that would put a point right here, and now my 2 points are from here to here. My h value, the difference between 2 and 2.001, 001, and the slope turned out to be 64.016. And then we said, hey, let's get even closer, 2.001, then 2.0001. What's happening here is the slopes of these tangent lines, not tangent lines, excuse me, the slopes of these lines going from between 2 points, as h approaches 0, because the difference between the starting time and the ending time is decreasing, so the h values are approaching 0 and the slopes are approaching 64. So we picked 2 points which represented 2 time values. Okay, so let me just summarize again what we just talked about. So we wanted to find a good estimate for how fast the rock was traveling at 2 seconds. And so in order for us to use the average rate of change between 2 points, we just decided to pick 2 times, 2 to 2.01. And we calculated the average rate of change, or the average speed of the rock between those 2 times, and we found it to be 65.6 feet per second. The difference between time 2 and 2.1 is 0.1. And so we did this several different times, for different times that were decreasing the difference between the times. So we wanted to get closer. We wanted to pick 2 values, or we were picking values that kept getting closer and closer to 2. What that meant is that the h values were all decreasing and getting closer to 0. All of our slopes ended up getting closer and closer to 64. So we can take this value of 64 as the speed of the rock at t equals 2 seconds. And so I'll actually write that on there. So the speed of the rock at t equals 2 seconds is 64 feet per second. So it's this average speed, or this average rate of change, or this value that we take as the instantaneous speed. I'm going to pull this previous page back over, and I'm going to comment on one thing, and then we're going to finish out this part of the lesson. So when I looked at, and when we worked with, let me scoot this up a little bit. Notice that when I drew my lines between the points, this line right, these lines, this is the line that connects these 2 points, and we can call that a secant line. A secant to a curve is a line through 2 points on a curve is a secant to the curve. So we can say that this is a secant line. As we chose a time that was getting closer to 2, the point on the graph and the distance between the 2 points began to get smaller. So the secant lines kept getting smaller. As h got closer to 0, the slopes of the secant lines were decreasing until ultimately we have a line that is indistinguishable from the secant line between 2 points that are very, very close to the point t equals 2. And we will continue with that thought in the third part of this lesson.